So second speaker is Anirban Basak from ICTS, part of TIFR, and he'll talk about pots and random clusters on locally tailored graphs.
Okay, so thanks Manju and thanks the organizer for the invitation. So let me start. So as the title says, I will be talking about mostly on pots and a bit of random cluster measures on locally tree-like graphs. Okay, and I'll explain what these terminologies mean as I go on. So first, let me straight away begin with the definition of the pots, which is a generalization of the easing that you have heard in the previous talk by Shushandu. So let's define this on finite graphs first. So in most of the talks, I will be focusing on graphs which converge to some trees in a sense, which I'll define as I go on. So first, let me begin with this definition of pots on finite graphs. So this is a measure on the vertices of these graphs, and each vertex can take one of these q colors, which is q is some integer, and it has two parameters. There's beta and b. So the beta is called the inverse temperature parameter, and this b is the external magnetic field parameter. And this has this Hamiltonian, which looks like this. So this delta sigma is sigma j. As you can guess, this is the indicator that your sigma equals sigma j. Okay, so this is your measure, and you need to normalize it to make it a probability measure. So this is a normalizing constant, and also commonly known in the literature as the partition function. Okay. So this you can define for an integer q for greater than or equal to 2. Okay, and a particular case which I've heard in the previous talk where q equals 2, so your spin can take only 2 values. And there is an easy correspondence to make this, from this measure to taking for q equals 2, where your spins takes -1, 1. You just make this affine transformation to to change your domain from 1 to 2 to -1 to 1. And probably more familiar framework for easing is to replace this delta sigma sigma prime by this 1 plus xx prime. So in the Hamiltonian, instead of this delta sigma 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 is sigma j, you can have, when your q equals 2, x prime plus 1, and this 1 you can absorb in the normalizing constant. Okay, so this means that for the easing, there is a slightly different representation, which is probably more popular, that your Hamiltonian looks like this. So your spins now take -1, 1, the value -1, 1, and the Hamiltonian looks like this. You have beta xi xj, sum over all the edges, over all ij in the H set, and then you have b times the sum over all the vertices. So this is the easing measure on a given finite graph. Any question about this definition? All right. So then let me say something about very one of the easiest model, one of the easiest setting in the easing model, where you consider this easing measure on the complete graph, which is also goes by the name Curie-wise easing. Okay, so so here I wanted to include this example because here you can do almost all the computation just by bare hand. Okay, so this will give an idea on what kind of results you would expect for a more general setting where you have more general graph, and but the tools will be completely different. But this will give you a sense what kind of results you should expect in the large general limit if you consider easing on a general graph. Okay, so here, as also Shushandu mentioned in the previous talk, let's say if your beta is 0, and let's say then you see from this Hamiltonian, this tells you that if your beta is 0, then the spins are basically independent. Okay, so and this phase is known as the disordered phase. Okay, and if your b is 0, then you don't have any bias towards any particular value of the spin. But if your b is positive, you put a bias on the +1, and if your b is negative, you put a bias on the -1. But if your beta is 0, all the spins behave independently of each other. However, if you look at the other extreme, where your beta is infinite, and let's say your b is 0 for the sake of discussion, then you see that your probability mass will be concentrated to those spins which are perfectly aligned. You would want your all xi's and xj's to be same. So this is the completely ordered phase, and what one expects for easing measure on complete graph is that if your graph is large, if your n is large, then there is a sharp disordered order phase transition. So there is a beta critical, the critical temperature, as one calls in the literature. If your beta is less than beta critical, then this is called this disordered phase. Your spins behave like independent variables. However, if your beta is greater than beta c, then all your spins tend to favor one particular spin or the other. So this your configuration space kind of becomes disconnected and puts most of its mass in two ordered phases, where most of the spins are either +1 or most of the spins are either -1. So this is the behavior that you would see if your beta is greater than beta c. So this is the called the low temperature regime, and this is the high temperature regime. Yes, it does. Yes, it does. That's a good question. So basically, what happens is there, for the easing, the interesting scenario happens when your b is equal to 0. But if you are in the Potts regime, your k is greater than 2, then there is an interesting regime also for b positive. So that's why I did not write b, the dependence of beta c in b. But that's a very good question. Any other questions? Yes. Yes, so that's also a good question. So basically what happens is that to get a non-trivial limit, you need to rescale your beta by something. And what goes in there is kind of the average degree. So if you want to define for a general graph, you should have the average degree sitting in the denominator. Any other questions or comments? All right. So as I said that the goal of this, including this in my talk, is that for the complete graph case, one can do explicit computation just by bare hands, and to show you what kind of results that you get by just computing various observables on this complete graph scenario. So the first thing that one needs to understand what happens to this partition function, because this is a very complicated sum, and you will see that once you understand this partition function, then lots of other properties of the measure also follows from that. Okay. So what can we say for this partition function in large n limit? And as the name goes in literature, this is called this asymptotic free energy density. So in this Curie-wise easing case, one can actually compute this asymptotic free energy density, which is given by this explicit formula, this phi star beta b, which is an supreme of a certain function, phi beta b m, and this has this explicit expression, and this h is just the binary entropy. Okay, so this is a very explicit computation. So how does one get this? Okay, so let me try to explain how does one get this in this Curie-wise setting. So this is a very easy computation. So you start with this this high school algebra trick that you are summing over all xi xj, I not equal to j, I less than j here. Then this is just 1/2 sum xi square minus 1/2 summation xi square. Now since my xi's are plus or minus 1, so this is just negative n/2. Okay, so what I have done with this computation is that I have replaced this quadratic term by the square of this linear term. Okay, so now I can put this back in my Hamiltonian here, and now I see that my Hamiltonian become just a function of this summation of the xi's. So now I can analyze this in a better way. So once I plug in that, then I look at my partition function, then it just becomes this sum. So I call this mn to be sum of the spins, and this is what I get in the Hamiltonian. And then you just compute, you calculate how many choices of the configuration that you have, which will give you this value of particular mn, and this will find out to be just n choose n plus m/2. So this is just a straightforward computation. And now you want to sum over all choices of mn over this discrete set, which are the possible values of your sum of the spins. Okay, now what you do, you just to have a bound on this guy, you say, okay, this is sum of non-negative terms, so this guy has to be at least as large as the maximum over all these things. Okay, and this gives you this bound. So how do you get this nice looking form? You just apply Starling's approximation there. That will give you this lower bound. And what is the upper bound that you get? Of course, it is bounded by the maximum of each of these terms times the how many such terms there are in the sum, and which is n plus 1. And so this has a nice lower and upper bound, which just follows from the straightforward computation. Okay, so this is the lower upper, which I rewrote again. And therefore, once you have this, then you see that if you want to take a log then these guys, and you divide by n, then these guys go away, and so on and so forth. So you just end up with this supremum over this function. And there's also one more step of approximation. Here you're taking this little m in this discrete set. You just go from this discrete set to this continuous set negative to 1 to 1. So there is another set of approximation going in. So this gives you this asymptotic free energy density. So this at least gives you an expression for what it should be. But this does not tell you, the picture that I told you earlier, that there is this sharp disordered ordered phase transition. So this follows from what happens to the supremum, follows from the behavior of the supremum. And there is a distinct behavior where your supremum is achieved depending on this beta and b. So for that, you just analyze this variational problem. So basically you solve where your derivative with respect to m is 0, and this turns out that your m must satisfy this fixed point equation. This your m is hyperbolic tangent of beta times m plus b. Okay, and then you need to do some calculus, and it follows that for beta less than equal to 1, there is a unique solution of this fixed point equation, which is denoted by m star beta b. And the important thing that I want to emphasize is that this m star beta b goes down to m star beta 0, which is 0 as b goes down to 0. So this happens for beta less than equal to 1. However, there is a different scenario if your beta is greater than 1. There are multiple solutions of this fixed point equation. Depending on your value of b, you may have a global maximizer, a local maximizer, and a local minimum. Okay, and out of these three, solutions of this fixed point equation, there is a one global maximizer, which we call this m star beta b. Is that this is strictly positive for all b greater than equal to 0, including the possibility that b can be 0. So you see in particular that there is a different behavior depending on whether your beta is less than 1, less than equal to 1, or greater than 1, even for the solution m star beta 0. So these are the two different, these are the indication of two different phases that arises in the easing on complete graph. Any questions or comments at this point? Yes, maximize is unique in both cases, but in the second scenario, if you look at this function, which is in the previous slide, it is symmetric. So if you plug in b equals 0, it is symmetric in m. So if so my m star beta 0 as well as negative m star beta 0, both of those two are maximizers for beta greater than 1. So you have two global maximizers for beta greater than 1 for b equals 0. But if you allow your b to be strictly positive, then always there is one global maximizer. Any other questions or comments? All right. So as I said that there are these two distinct phases. One is this ordered phase, which is characterized that m star beta 0 is strictly positive, and it happens when beta is strictly greater than 1. Other is the next. This other phase is called the disordered phase, which is when your beta is between 0 and 1. And what happens in these two different phases? This is given in this following description of the spin magnetization, or the sum of the spins. So if you look at this sum of the spins, you take an average. Then if your beta is less than equal to 1, let's forget the case b greater than 0, then it says that, as we know that m star beta 0 is 0 there, so it says that your mn over n, the average of the spins, has to be very close to 0. And that happens with exponentially high probability. However, if your beta is strictly greater than 1, then there are two different locations where your average concentrates. So it could be either m star beta 0 or negative m star beta 0. Both are non-zero, so your entire configuration space kind of decomposes into two distinct hubs, if you can say, and your average your average spin configuration kind of concentrates into these different hubs. So any questions or comments about this? All right. So this is just to give an illustration what kind of disordered ordered phase transition happens in this easing or its generalization to the Potts model. But this is what I did on what I showed only for the complete graph. But For the rest of the talk, I will not focus on this complete graph case. I will, once you have this upper and lower bound, you can figure out what the constant should be. But I mean, definitely there are results. I do not remember top of my head. There are definitely some results for the CFC, but I don't know if they're optimal ones. Meaning that can you find a large deviations here? But so I believe there are results, but I don't remember the reference top of my head. Yeah. It will be complicated, but there are. Yes. Any other questions? Okay. So let's skip this. So in the rest of the talks, I'll focus on graphs which are locally tree-like. And what do you mean by locally tree-like graphs? So first, let me start with a very informal definition, and then I will make it precise. So what it means that if you have a graph, then let's say you position yourself at any vertex, and if you look at the local neighborhood, then that local neighborhood should be like a tree, meaning that it does not contain a cycle, and it should happen except for a vanishing fraction of the vertices. Okay, so this is what you say your graph to be locally tree-like, that for most of the local neighborhood that you find, if you situate yourself at a randomly chosen vertex, you should not see a short cycle. So how do we make it precise? So we say that a sequence of graphs Gn with vertex at Vn and En, and most of the talks I will focus my Vn to be has cardinality n, so you can just relabel the vertices from 1 to n basically. And we'll say that it converges locally to a possibly random tree. I'll give you examples which has certain distribution. If for any given tree, if you look at the local neighborhood around this vertex, chosen vertex I of radius t, it should be isomorphic to some given tree of depth little t, t0. And if you take an average over all the over all the choice of the vertices, then it should converge to some limit, which is the given by this law of the limiting tree. Okay, and I should also mention one more point, that these isomorphism are rooted isomorphism, meaning that each of this tree has a distinguished vertex, which I denote by root, which I call to be root. And when you looking for an isomorphism, your vertex I has to go to the root of this tree t0, and then so once you fix the root, then you look for isomorphism between this bit and t0t. So this is what do I mean by rooted isomorphism. Okay, so and I'll use the notation Gn converges locally weakly to t if this thing happens. Yes. So this is my notion of converging a sequence of graphs to locally to some tree. So now let me give a couple of examples. So one of the most straightforward examples one can look at is that where GNs are uniformly random d-regular graphs. And what do you mean by that? You have the collection of all d-regular graphs on n vertices, and then you pick uniformly at random from that ensemble of graphs, and that is your GN, that your random graph GN. Then one can show that in this setting, your GN converges locally weakly to this infinite d-regular tree. Okay, so it needs a proof, but one can prove it. Yeah, so n is the number of vertices, and then you let n go to infinity. And second example that one can think of is the GN is the heterogeneous graph on n vertices with h connectivity probability lambda over n. So meaning that you pick any pair of vertices, you draw an edge between them with probability lambda over n, and then one can show that this GN converges in this sense to this Galton-Watson tree where the offspring distribution is Poisson lambda. Okay. So these are the two things these are things that one can prove, and there are many more examples one can construct. So any questions about this definition or these examples? Okay. So now, as the title of my talk says, that I'm going to consider pots and other measures, random cluster measures, namely on locally tree-like graphs. So since this graphs converges to this infinite trees in my setting. So I need to define what do you mean by pods on infinite graphs. So far I have given a definition on pods or pods on finite graphs. Now I'm going to define pods on infinite graphs. Okay, so there are many ways to define pods on infinite graphs. So this is, so this is one such way you can define, and this is the only thing that we're going to talk about. But of course, there are other ways to define this as well. So here is what I do. So I take my infinite tree, I truncate it at depth little t, and let's say this piece is the subtree of that of depth little s. Then what I do, then I assign my spins to be k on the boundary of this at depth little t. Okay, so this creates a measure on this finite tree, which you know how to define. And once you have this tree, when I condition on the spins to be little k on this boundary or on the leaps at level t, then this will induce a marginal on this little subtree of depth little s. So which I call this by mu kt beta bs etc. Okay. Then I let my depth little t go to infinity. Okay. So if the limit exists, then this gives a measure again on this little subtree, which I denote by mu k beta bs. Okay. So first I fix my little s, then I take any little t greater than little s. I condition the spins to be k on this leaps at depth little t. Then I let this boundary go to infinity. Okay. So if the limit exists, then I define these measures, and one can show that limit indeed exists in certain cases. So for example, if my k is 1, so I fix all my spins to be 1 at this boundary, then the limit indeed exists for any choice of beta and b, non-negative. And additionally, if you tell me that my b is 0, so there is no external magnetic field, that for any k 1 to q, the limit exists. Okay. So once this limit exists, as I said, this mu k beta bs, they are still measures defined on this subtree of depth little s. Now, however, this one can show they give you a consistent marginals. So therefore, you can use these marginals to determine a measure on this whole tree. So this gives you a measure on this infinite tree, and each of the vertices again take the spins from 1 to q. This is how we define infinite volume pods with a given boundary condition k on the infinite tree. Is the definition clear? All right. So there is one more thing that you'll need. So instead of putting k, the spins to be k here, the one thing that we also need, we put the spins to be IID uniform on the discrete interval 1 to q, and this is known as the free boundary condition. So the pods with the free boundary condition. So again, we do the same exercise. We get this mu free on this mu free s on this finite trees, and then again these marginals are consistent, so that give rise to pods, infinite volume pods with free boundary condition on the infinite tree. Okay. So next, let me tell you something from statistical physics. So if you find this thing bit too heavy, just stop me and ask questions. Okay. So what statistical physicists do, they have a lot of heuristic approaches to give you certain predictions what should happen if you look at a sequence of graphs converging locally to some tree, not necessarily regular tree. And if you consider various kinds of models, such as pods is one such model, and their predictions of what should you expect if you look at the large n limit. And to describe such limit, they have certain procedure which goes by the name cavity method or the replica method. So I'm going to try to explain what are these predictions are, and then we'll see later in the later part of the talk that one can actually mathematically, one can actually rigorously prove those predictions. Okay. So first I start with this what is known in the literature as the Belief propagation map. So what is this? So this is just a map. You take any probability measure on the discrete interval 1 to q, and it spits out again a probability measure again on the same discrete interval 1 to q. Okay. So this is just the map. Okay. And how does this relate to the pod setting? So if I go back, suppose I put my spin values on this boundary, then this will induce a marginal on the levels above it. Okay. So now if I look at the marginals, which take any vortex which sits at the level t-1 and try to compute what the marginal should be. Now recall that this is a deregular tree. So meaning that every vertex here except the root has d-1 children. So if I try to compute that, if I put, let's say, spins nu, some distribution nu for the spins at each of these leaves, then it will propagate to some marginals here, which is just a parent of this, let's say, d-1 children, which are the leaves. And if you think for a moment, this is precisely what you get. Okay. So because of the Hamilton of the pots, this is precisely what you get if you put measures nu independently at each of the leaves at level t, and this is the marginal that you will end up for the for the vertex which is at level t-1. Okay. So this is the Billy propagation map, and there are two fixed points of this map which are of interest to us. So one fixed point is that, so you look at the limits of successive iterations, one starting from the uniform probability measure and another starting from this probability measure supported on spin 1. And as you can probably guess that this will be related to this mu free and this mu 1, because if you start from this, let's say, measure supported on one on these leaves, and if you propagate that using the Billy propagation equation or the map, then you end up getting ultimately here what should happen at the children level of this of the root. But there's a difference from going from level t to t-1 and going from level 1 to 0, because the root has d children, whereas any other vertex has d-1 children. So to go from the first level to the 0th level, you need to change the equation. So you need to change this d-1 to d. So that is the change that you need to do. Once you do that, then you end up getting this mu free and the mu 1 that I defined earlier. Okay, and let me just briefly mention that. So this is already complicated, so I don't want to go into too much detail in this. That here I defined this BP. So the rationale was that for each of these leaves, I put nu, the same measure nu, for each of these leaves, and then I get this BP map. And instead of putting nu for every children, I can do nu1 through nu d-1 rather, for different child of the same vertex, and that will give us a Billy propagation map which has inhomogeneous entrance law. So this, you can think this nu to be as an entrance law, and one can show these Potts gives measures on the infinite tree are basically those which are the fixed points for this inhomogeneous BP map. So I'll not go too much in detail, but one can prove that. So I'm not sure what to mean by resampling here. Any other questions or comments? Mm-hmm. Yeah. Mm-hmm. Yeah. Yes. Yeah. So the global dynamics, yes, those are related to this these fixed points as well. I mean, if it is going to be slow or fast, so it depends on whether you have two fixed points or you have unique fixed points. So that depends on that. So yeah, so I mean, this phase diagram is kind of gives you various information, whether you want to run this global dynamics or run this SW chain. So those things are all interconnected. Okay. So now here is a prediction from the statistical physics literature, that we define this this BP map, and then you define what is called this Bethe free energy, which looks like this. So I'm not going to explain why it is like this. And the Bethe prediction says that if you look at this log partition function, then it has a limit, and the limit should be given by the supremum of the Bethe free energies, where you take a supremum for all fixed points. This is BP fixed points. Okay, so this is a highly non-trivial prediction, and there are some reason behind it. So, for example, what I can say in one sentence that if you look at this log Zn, or rather in this partition function, if you assume that your Gn is actually a tree, then this is what I wrote here is exact for certain nu. Okay. So the idea is that if your graphs locally looks like a tree, then you should kind of get back the same picture. So I don't know if it makes sense, but I.
So what is this prediction for GNs which are converging to?
Okay, so the prediction that I wrote here is for Gn converging to the regular tree, but one can make same prediction if your tree is non-regular. So even in that scenario, there are predictions which looks like this. But this prediction that I wrote here and the BP map that I wrote here are for the case where your tree is the deregular tree. And one can define similar in analog for the non-regular setting, but I did not write that in that generality. Yes. Yeah. Yes. But you can also define, so you may have that some vertex have D children, some have some D prime children. You can also define in that setting. Mm-hmm. Yeah. Yes. Yeah. Yes. Any other questions or comments? Okay. So what people have proven that, so one can actually characterize what is this supremum of the fixed point of the Bethe free energies, and in this in this regular setting, this is just the maximum of the two fixed point that you defined earlier, this nu f and the nu 1. And if you remember that nu f was the this limits of BP iterations where you start from this uniform probability measure, and the 1 was the where you start from Dirac at 1. And this is this rightmost inequality is proved for any beta being non-negative and D greater than or equal to 3. One can prove that. However, this left equality is harder to prove, that it is actually equal to the supremum, because once you are at this middle quantity in the display, then you can actually do lots of calculus and actually show that this is actually the case. But to prove that this convergence holds, it requires different approach. So there have been several progress. So the first, let me mention that for the Ising scenario, it is much simpler, and one can actually prove this conjecture in much more generality. Your graph need not be, your graph need not converge to a regular tree. For example, you can take graphs which are Eddowes-Cheney, and you can have the limit to be alternate. So even in that scenario, you have this prediction proven for the Ising setting. However, for the pot setting, it is much more difficult, meaning that Q greater than or equal to 3. So first, it was proved by Dembo, Monterey, Sly, and Son back in 2014. They required that D to be even. And then the last couple of years, there have been a couple of improvements. So the first, on both these papers, consider the case where B is equal to 0. In the first one, they require that this is deregular and edge expander, and they need some bounds on D and Q. And this is improved later by this second paper by Banks, Borbeni, and Sigveri, where they require this deregular. So this has been, so people believe this is true, and this has some some partial proof of this conjecture. Okay. So now let's see what it means pictorially. Okay. So as I said that this supremum is given by this maximum of these two Bethe free energies, one at the free boundary condition and one for the one boundary condition. Okay. So what happens? So let me explain what this picture tells us is that, so this white region that you see, there your nu f and nu 1 is the same. So you have a unique global maximizer and unique fixed point, rather, to be precise. Shaded region, you do have multiple local maximizer. In this RF region, the free one has the largest Bethe free energy, and in the R1 region you have this new one which has the maximal Bethe free energy, and on this critical line both these two coincide. So this is what happens in the POTS setting, and this is much more delicate than the Ising setting. So for the Ising case, what happens is the following. So there is some beta critical, and above this beta critical you have two. However, rest of the plane you have only one local maximizer. Okay. So this is slightly much simpler than the POTS case, where you have a genuine genuine two-dimensional region where you have multiple stable fixed points. Okay. And also the one more thing is that in the Ising setting you have the so-called the second order phase transition here. However, here you do see a first order phase transition. And one more thing I want to mention for the experts that in the Ising, both the uniqueness and the non-uniqueness transition as well as the disorder order phase transitions are the same, which happen as beta critical, but here they are different. So for example, in this point here, where this beta F curve meets the B equals 0 line, you see a uniqueness non-uniqueness transition regime change, and here in this where this beta critical curve meets, there you see this disordered order transition threshold. So things are different in the POTS and the Ising setting. Mm-hmm. 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 Yeah. Yeah, so basically what we'll see in the limit that whatever maximizes here, you will find it in your limit. So this is what you're going to prove actually. Any other questions or comments? Okay. So next, as I said, that our goal is to to study the limits of these measures. These measures on the these are POTS measures on the graphs GN, which is converging locally to this infinite irregular tree. And what statistical physics tells us that it is some mixture where the mixture probabilities are these fixed points which maximizes these Bethe free energies. Okay, so it means that if you have unique maximizers, then your limit is just given by that unique global maximizer. However, if you have a multiple global maximizer which happens on this critical line, as I said, it just tells you it has to be a mixture of those global maximizers. Okay, so again, let me make a very vague remark. So the prediction that I wrote here for the limits, but also there are predictions what happens for this relative weight of the spin configurations when you condition to be close, when you condition yourself to be close to a local maximizer. So in that setting, what the relative weight of this spin configuration should be, it also given by this so-called this the Bethe prediction. I mean, one can write down what it should be, but so I'm not going to write it down. And there has been some recent progress by this in this paper for B equals 0 and when Gn is again uniformly random irregular graphs. Okay. So now, as I said, I need to talk about this sequence of measures on this finite graphs, which are POTS measures, and then I'm going to study the limits, which should be the infinite volume POTS measures. But first, I need to define what do you mean by convergence, because I am starting with measures on finite graphs, then I'm talking about limits which are sitting on this infinite graphs. Okay, so first again, let me start with this informal definition. So what you do, you again position yourself to any randomly chosen vertex, and you look at the distribution that you see around yourself in a finite local neighborhood, and then you want to say that for most of the choices of the vertex that you have in your graph, this distribution is going to converge. So this is what I mean by this local weak convergence of measures. Okay, so I can make it precise. So what I do, so I fix my vertex I choose the radius of my local neighborhood, this t, and then I look at this joint law of this the neighborhood and the spin configuration on that neighborhood. Okay, so this spin configuration, the law that you put is coming from the measure that you put on this entire graph, the spots measures. Okay, now I pick my this vertex I to be random. So I pick any random vertex that I see. Now this should induce a random probability measure, which I denote by this PNT I sub n. This is random because my vertex that I choose in my graph is random. Now note that if my Gn converges locally to this infinity regular tree, then this first marginal, which is this BIT, has to converge to this Dirac at this first generations of this infinity regular tree. Okay, so given that what you have is that this, if this guy PNTIN converges, the first marginal has to be this Dirac, and the second will be some measure which is the T marginal of this random probability measure. Now note that, recall that again, that my my PNTIN has two components. The first coordinate is this, the local neighborhood, and the second one is the spin configuration. So if I look at this M, or this second component, this has to be a probability measure on the measures on this spins on the infinite tree. So if this happens for every little t, then you declare that your sequence converges locally to this random probability measure M. Now, if your random probability measure M is not really random, is a Dirac at some probability measure, then you say that this converges locally in probability to this measure mu, and this will denote by this notation mu n converge locally to this mu. So is the definition sort of clear? Okay, so if this is not clear, so I would suggest that go back to this informal definition, so you can view it what happens here. So you choose a random vertex and you look at any fixed local neighborhood, and you want to study the distribution that you see around in that local neighborhood, and that distribution, if the distribution converge for most of the choices of your vertex, then you say that your measures converges locally. Say that again. Yes, you can say that. Yes, definitely you can view in that way. So, but the measure that you are putting on the colors coming from the pots. Yes. So in my talk, I'm taking Gn to be deterministic. So Gn can be random. So if it is random, what you do, you fix and you take your favorite realization, you do it for that realization. Yes. Any other questions or comments? So basically, what happens if you let's say if your Gn is uniformly random irregular graph, then it happens for almost every realization. Yeah, asymptotical. Yes, asymptotical. Any other questions or comments? So the thing is that you need to define the notion of the infinite volume pots for that graph one. So this I don't know. Maybe there is some notion. So once you define that notion, definitely you can extend this kind of predictions for that setting as well. All right. So let's see what we get. So so now let me formally state what are the assumptions that we work with. So we'll assume always that this Gn converges locally to this infinite irregular tree, as well as we'll assume that this Gn is uniformly sparse, meaning that its degrees are uniformly integrable, and this allows us to compute the expectations of several observables in the limit. So this is just a technical condition, and then we'll assume that we have this statistical physics Bethe prediction that 1/n log Zn has this expression. As I said, that it has been partially proved for many cases, except the case when d is odd and b is positive. So then it is really an assumption. Otherwise, this has been proved. Okay. So once you have these assumptions, then you have this picture. So maybe, okay, so. Yeah, yes, right, right. So, okay, so this is what you get. So let me go back to the next slide and then come back. Okay, so this is what you get. So in this white region, which is unshaded region, you have this free measure and this W measure. This is mu W, which is need to define. So basically, the thing is that if your B is 0, then then you can flip the then the distribution that you get for the spins is independent of any permutation that you do. So therefore, the limit, it has to be, if there is a limit, it has to be a symmetric mixtures of this k boundary condition spots on the infinite tree. Otherwise, if your B is positive, then you favor the spin 1. So this mu W has to be just the mu 1 beta B. Otherwise, for B 0 has to be a symmetric mixture. Okay. So if you define this mu W in this way, then what it tells you that if you're in this white region where your mu F is equal to mu W, there you find the limit to be this mu F. If you're in this R free region, so if you remember here, this slightly shaded gray region, the free Potts measure has the larger Bethe free energy. So here, what you find the limit to be just the mu F. On this line mu W, on this darker shaded region, the Bethe free energy corresponding to the mu 1, which is same as mu W here, has the larger Bethe free energy. So here the limit should be, we prove that limit is given by this mu W, and same on this line, we need to modify the definition of this mu W. And on this critical line, what you can prove is that any limit points that you can find has to be a mixture of this mu W and this mu free. Okay. So this is what I wrote here in this long slide, but this is pictorially, this is what we have proved. And we could not prove in this case the case where it is B 0 area on the critical line, so on this critical point. So our theorem excludes that. So this is the result. Any questions about this? No. So this will come. I'll come to it in the next slide. So believe that should depend on the graph sequence. It is not an. So it is not a universal mixing coefficient. So it basically depends on the short cycle structures. So it depends on that. At least it depends on the how many short cycles you have. So this coefficient alpha depends on that. So basically now let me go to the Riemann association is pointing out that that our theorem does not include this critical point on the B equals 0 line, and there has been some proof by this paper by Helmut, Jensen, and Perkins, where they show that this mixing coefficient is a genuine random variable which depends on the distribution of these short cycles on Gn, and they take Gn to be uniformly random due to regular graph. So it is some function of the underlying Poisson random that you find coming out of the short cycles. And also I wanted to mention that this part 3 of the theorem where we consider on the critical line, so this result does not tell you that the limit point that you find is a genuine mixture. It just tells you that it is supported on this convex hull between this mu W and mu F, but it does not tell you it is a genuine mixture. And it is indeed a genuine mixture for the case B equals 0 and this more restricted setting done by Helmut, Jensen, and Perkins. And we believe that this mixing coefficient alpha should depend on the graph sequence. So it is a non-universal in that setting that you need more information, just than saying that your Gn converges to this deregular infinite tree locally. Any questions or comments? Okay. So what one can also study, what is known as this pure state decomposition. What one does, you now want to consider pots where you fix the dominating color and want to see what happens to this measure. So you define your script kappa script kn to be the one which is the dominating spin value, and you take the conditional Potts measure where you condition on the spins to be dominating. So basically what happens, if your B is 0, then you know that the pot's configuration is free, is independent of any permutation that you put on the spins, because of symmetry of the Hamiltonian. So you need to break this symmetry of the spins on the line B equals 0, and then you need to see if anything changes for this pot's measures, and if this converges to some pot's Gibbs measures in the limit. So what one can show in this setting is that, so first let me go through the statement of the theorem, and then we'll come to this extra assumption that you need for the expander graph. So if you're below this critical value of beta, then you recall that this mu n without this conditioning converts to this mu free. So it tells you that even after conditioning, that even after you condition the dominating spin to be k, this spot's measure, this spot's measure, it still converges to this mu free. However, if you are above this beta critical, then this conditioning will push to one of these pots on the infinite tree with a given boundary condition. So it basically above this critical temperature, this conditioning breaks the symmetry. Okay, and you need some condition on the graph. You need this graph to be age expander for this result to hold. And what is this age expander? Tells you that. So informal. So let's not go into the formal definition. So it tells you that if you give me any two subset of if you give me any subset of vertices, then there are a lot of edges between that vertex and its complement. So basically that assumption. So it means there is no bottleneck in a graph. Okay, so this is what we get for the pure state decomposition. Mm-hmm. Mm-hmm. So this we don't know. So for the easing, I think because of the tree structure, you can always have a decaying correlation. Yeah. So this, yes. So but for the pots, we don't know what will happen. So I have 8 more minutes. So okay. So I'll try to explain. What are some of the ideas. So I'll just explain. I decided to explain only one. So the one where you look at this conditional pot's measure below this beta critical, and you want to claim that the limit is still the free pot's measure. So what we first notice that this mu n beta 0 you can write as this symmetric mixture of this conditioned pot's measure, and this is again due to the fact that the pot spin configuration is for b equals 0 is is independent of any permutation that you put on the spins. So therefore it becomes this symmetric mixture of this conditioned pot's measures. So basically what we have is by the previous theorem that this mu n beta 0 below this beta critical converges to this free pot's measure, or with the pots with a free boundary condition. So because of that, you just need to show that this, if you take two distinct colors, K1 and K2, and if you look at this difference between these two conditional pot's measures, then the difference goes to 0. Then from this first line you get, and the second line you end up proving the result. And how do you prove this result? You basically do via coupling. So what is the idea behind, what is the idea here is that you produce two pot spin configuration, sigma 1 and sigma 2, such that they agree on a set with high probability up to little order in many sites, and as well as you can switch the dominating color. So this is the very rough idea, but it needs several steps. So I think I should not go too much into details. So it involves this complicated way of generating an IID uniform, which you can read from the last line, but it is slightly complicated. So the script kn is the defining. Okay, so it is the dominating color for this spin configuration. So if I go back, so this is the argmax of this guy. So basically, if you give me a spin configuration, so it will spit out an integer between 1 to q, which will be the dominating color for that entire spin configuration. Hmm.
Can you do the switching among like multiple places together?
Yes, I mean you can do that. Yeah, yes. So this you can do. This you can definitely do. Yes. Any other questions or comments? Okay, so as I was saying that, okay, so there is this lemma, which is basically a graduate level probability exercise, I would say, or maybe also undergraduate level. And so it is basically, generates a bunch of ID discrete uniform random variables via this method. And the consequence of this lemma, so again, I'm skipping a lot of things, is that if you switch two colors, then you create another IID sequence of random variables so that the difference, so that the sites on which they differ is not too much. So this basically gives you the coupling, and then you need to introduce random cluster measure. So I'm trying to avoid this at the moment, and combining these two. Also, you need to show that there is no infinite cluster for the free random cluster measure below this beta critical. Combining all these three pieces, you end up getting this. So I'm skipping a lot of, so I skipped most of the things in the proof idea, but I will be happy to discuss this offline. Thank you. I'll stop here.
Questions?
So you are using that expander property that so where do you use that, like for the Billy propagation
No, so the
things?
thing is that, I mean, so expander may be too strong, I mean, possibly a too strong assumption, but what you really need that, so let's say if your graph has discrete components.
Yeah.
So if you condition that your dominating color in the entire graphs, so for the entire spin configuration is some, let's say color 1, so it does not restrict your discrete components to act independently. So it might still be true that your smaller discrete components has a different dominating color, but overall you have a you have a different dominating color. So you need some kind of connection between this discrete component. So if I go back, so you see that this assumption is needed when you're above this beta critical.
Yeah.
So basically, if you want to say that your entire measure, even if the conditioning goes to one particular POTS measure with the given boundary conditions, this will not happen if your graph, for example, had discrete component. So you need some kind of connectivity among these discrete components. So this comes in the proof of that, which I did not show. But this basically so the intuition is this, that if you have discrete components, that even if you fix the dominating color for the entire spin configuration, your different smaller components could have a different behavior. So you do not know that that in each of your discrete components has to show up and has to give you the same POTS measure in the limit.
Okay.
So this is intuition. Yeah.
Okay, and the other thing that I was thinking is that for this the previous result that you were using for you were showing for deregular graphs.
Yeah.
So is this for, I mean, does this extend for other graphs also?
So it should, but it is not known.
Okay. Thank you.